Hey all, it's Mr. Yeager for chemistry, looking at hopefully a fairly quick section on entropy and Gibbs free energy. So essentially we have already been talking about thermodynamics, thermochemistry, and again the reason we're looking at this is why do the reactions end up occurring, or why do we have to force the reaction to occur? So are they favorable or not favorable? We already pointed out how enthalpy will affect whether it's favorable or not favorable. A negative enthalpy supports a reaction to occur. A positive enthalpy actually does not support a reaction because we have to add energy to it for it to occur. Okay? There are two other aspects to this though, all right? And they are called entropy and Gibbs free energy. So I'm going to start off with entropy over on the left, and you can kind of see my picture there trying to show what entropies we're showing. It's complete kind of chaos. Entropy is the measurement of what we call the disorder of the system, all right, or a particular situation. What the heck is disorder? Basically the idea of how much is the system just freely moving around, or how much structure did I force into the system itself? How much did I force these chemicals to come together and stay together versus possibly letting them be very, very free? That is a measurement of their entropy. All right? We can actually calculate it out similar to how we calculate out enthalpy, all right, with like a similar kind of Hess's law setup. There's also some other separate calculations you could do as well in terms of how to measure the entropy, but that's very much getting into what's called physical chemistry, which is definitely a higher level chemistry course in college. What I need you to know is that it turns out that the universe supports or wants to have greater disorder, all right, which again we could get into the idea of like philosophical conversations with that, but we're again looking from a scientific standpoint. From a scientific point of view, science wants greater disorder that supports favorable reactions, okay? So, while there is a calculation like I already said, the only other part I want you to understand is to be able to have a question on a test and go, hey, you have a negative entropy. And again, entropy, the symbol for it is S, that was shown above, all right? If I have a negative entropy, will the reaction be favorable or not favorable? So in this case, negative means not favorable, positive means favorable. Positive S means you are increasing the disorder in the system in the chemical reaction. Negative means you are decreasing the disorder. What would I actually be looking for in chemical reactions to determine whether I'm increasing or decreasing entropy? Part of it would just be what state of matters do you have, okay? So if you have a solid, which I'll call S solid, versus a gas, these two states of matters have very different entropies. The entropy of a solid will be much less than the entropy of a gas. Why? Because you are forcing those chemicals to be in a particular spot, and all they can do is stay in that spot and vibrate. You are keeping the system together. You're keeping the structure of it. While a gas has no structure. The particles are completely freely moving around. So it turns out, if possible, atoms would love to just be completely free of each other. All right? That would be the goal in some sense. Now the crazy thing with this, as we're going to see, is there's going to be a balance between the amount of disorder and the amount of heat energy needed to maintain that disorder, all right? And that's where we have kind of a juxtaposition between the two to try to say, what do I need to have? And I need to balance these two things, the enthalpy and the entropy together. And what ultimately does that is what's called the Gibbs free energy. And the Gibbs free energy is finally a measurement of how favorable a reaction is based on the conditions given, okay? And what I mean by the conditions, what's the enthalpy that's occurring, what's the entropy, and then temperature actually plays a role as well. How much is the temperature around the system, obviously trying to add energy into it or decrease the energy involved. It turns out the more negative the Gibbs free energy, the happier the chemicals are in the system. We want to have as low a negative Gibbs free energy as possible, which again is a balance between the energy aspect, the heat energy, and the entropy together. So a larger negative G is favorable versus a positive G is not favorable. All right. There is an equation that puts all three of these things together, gives free energy, enthalpy, and entropy. It is delta G equals delta H minus T delta S. And this is your official Gibbs free energy equation. I'm not going to have you use it. I kind of just want to point out how this kind of works and where you can see how everything would be supporting each other. So you can see if we have a negative H, we should hopefully already have a negative number here. And if I have a positive S, if I subtract a positive number, remember I basically am adding a negative, okay? I have to do the opposite with it. And you can see how temperature is involved, okay? And so that would lead to a larger negative delta G or Gibbs free energy involved in the chemical reaction. So a positive S and a negative H supports a negative G, okay? Negative H and a positive S. Okay, but you could get a situation where it's like, hey, maybe you have a small positive delta H here, but then fortunately you have a large delta S, positive delta S. So if you have a positive and you subtract another positive from it, obviously it would become possibly negative, all right? But this is where you could have ones where it's like entropy-wise, it's not supporting it, but enthalpy it is. But ultimately, what's the delta G in the end? What would the delta G be in the end with that chemical equation? So this is something, if you go into higher level chemistry, you will absolutely be using this equation quite a bit to determine the favorability, the spontaneity of chemical reactions. All right, thank you very much.